Okay, so good afternoon, ladies and gentlemen. So today we have a speaker, Florian Oschmann. Let me just introduce him. He did a PhD with Petr Bela in University of Dortmund. And then, because there is this close collaboration between Prague and Dortmund, and in the past it was with Leipzig. So because of this, Florian came to us, to our institute, and he is working with, let's say, concerning compressible fluid, because in Prague we are mostly compressible. And also, we start also to work about the problem of collision with this full structure interaction problem. But today he will speak about homogenization, and it is, let's say, some insight in homogenization of compressible Navier-Stokes equations. So please, Florian.
Okay, thank you, Shaka, for the introduction. And well, yes, compressible Navier-Stokes equations, you probably all know, or at least have seen. I would like to make it quite general, and you will not see many equations and not see many proofs, but rather many pictures. And this is joint work, of course, with Shaka and also with Milan. So essentially, I will present two results in here quite recently. And to start, just let me introduce what we are talking about. And what we are talking about is precisely, let's say you have a bounded Lipschitz or smooth domain, as you wish, in 2 or 3 dimensions in RD, and we perforate it by some small bolts or some particles inside, if you wish. And inside of this, we consider the Navier-Stokes equations for now, let's say incompressible or compressible, as you wish. And these holes are, for simplicity, situated on the grid in ZD with some radius, which for some reason I will not explain in a deeper way, is in 2 dimensions exponentially small, and in 3 dimensions depends like a polynomial growth, let's say, on the distance of each particle. And of course, what we want to have is we want to send epsilon to 0, and when what you get is, okay, these small balls become smaller and smaller, so finally you will get a homogeneous domain. That's nothing surprising. But of course, you will ask, what are the governing equations in this system, or in this limiting domain? And it turns out that it heavily depends on this shape parameter alpha, which you can see here or here in 2 or 3 dimensions. And to motivate it, what shall you expect? Well, let's imagine the holes are very large. That means they put extremely high friction on the fluid, and finally the fluid will stop. So in the end, you will see no flow, nothing. But you can see, if you rescale everything, the velocity and stuff like this, that you can get some limiting behavior of this rescaled velocity, and what you will finally find is so-called Darcy's law, which is a particular situation of the porous medium equation. I will not talk about this, just to say what happens. And you see here, this happens precisely if the shape parameter alpha is strictly less than our dimension. Now, if the alpha is equal to the dimension, then the holes will still put some friction on it, but not too much to completely stop the fluid. So you will get essentially the same equations back that you had before, plus some extra term, which is then the so-called Brinkmann term, which is kind of in between the original Navier-Stokes and the Darcy law. But I will also not talk about it because it's a critical case. So it's kind of the most hard case, or the hardest case we can imagine, but we make our life simple, and we say, okay, we have very small holes, and essentially what you will expect is nothing. So in the end, you will see the same equations which you started with. And this is precisely what I want to talk about. And of course, I have to introduce the Navier-Stokes equations just for completeness, if you wish. So let's say we have a bounded Lipschitz domain in RD, and we perforate it, as I showed you, and in there we have the standard formulation of Navier-Stokes, meaning conservation of mass, conservation of linear momentum, some Dirichlet boundary conditions also on the holes, which will be crucial in the end, and some initial conditions on the density and the linear momentum. And in the above, we consider compressible stuff, meaning our pressure depends like a barotropic law on density. And for simplicity, we say our external force up here is bound in L infinity. Simply think of gravity. Moreover, we will consider Newtonian fluids, meaning the stress tensor is given by this relation. And finally, we get our initial data are as you expect. So L gamma for the density, and the momentum shall be in this space, which essentially comes that you say, okay, our density lives in L gamma, our velocity lives in L2, so our momentum shall be in this space. That's everything. And still the question is, what happens with all these equations if epsilon goes to 0? And for this, let me give you some results that are quite well known nowadays. The probably first thing about this, at least in full description, was the PhD thesis by Gregor Haller in 1989 or 1990, where he considered all dimensions, so not just 2 and 3, but really everything, and all values of the shape parameter. And then he gets precisely what I showed you before. So Darcy's law, Brinkmann's law, and the Navier-Stokes equations back. So for incompressible and stationary equations, essentially everything is known. Now for incompressible in stationary cases, to the best of my knowledge, we just have results for 3-dimensional case. And shortly after last PhD thesis, Mikulic showed the convergence result for alpha equals 1. Then White, Late, Fader, Feyreisel, Namleyeva, and Nečas showed the critical case, and the picture was completed by Liu and Yang in last year. So to say for the incompressible in stationary case, also everything is known. The compressible case is much more involved. And for this, many people have worked on this, and it's mainly in the 3-dimensional case, because there you kind of have, how to say this, some kind of fixed range in which you can work with for some, let's say, Sobolev spaces and Sobolev embeddings and so on. It's a little bit easier. And the main case is how I will present the simple case somehow, which was done, for instance, by Diening, Feyreisel, Lu, Schwarzer for the compressible, for the in-stationary case. Takeo Takahashi did, if I think right, also on this, and many, many people more. Milan, of course, also, and all the stuff. And to the best of my knowledge, there's just one work for alpha larger than 3, meaning large holes, which was done by Höfer, Kowalczyk, and Sebastian. And we adapted it together with Peter to also the critical case in 3 dimensions, but it's not exactly what I showed you before, since we need an additional assumption on the pressure law that is so-called below Mach. Essentially what it tells you, you start with a compressible system, you put the pressure extremely high such that it wants to avoid density fluctuations, and finally you end up with an incompressible system. And for incompressible system, everything is known. So this is, to the best of my knowledge, everything we have for this. And for the 2-dimensional case, Nečas and Pan showed it last year for the stationary 2D model and also small holes. So this is a brief overview of all results we have. And of course, now you can make several generalizations, e.g. Navier-Stokes Fourier equations for heat conducting fluids like Milan did with Liu, or with his PhD student Krzyzewski. You can randomize holes, so the positions and also the radii of the holes, which is essentially the part of my PhD thesis. You can do inviscid limit, which, for instance, Richard Höfer did, and much more. So you can generalize it in a quite large sense. But of course, there are some things to think about it. And people who know me know that I like this picture, so I insert it everywhere I can. Because for me, it kind of fits to all days mathematicians' life. So totally, I like it. And that's why I put it here. And now we consider compressible stuff. And recall that our pressure is given by this barotropic law. And if you follow all the proofs or the papers, you will see that the in-stationary 3D case needs this gamma strictly larger than 6. But for the stationary, you just have gamma larger than 2. If I don't know whether there are physicists inside here, they will say, well, it's still out of the range of physics, because from physics it shall be between 1 and 5/3, but well, we are mathematicians, we don't care about physics. So there's a huge gap between these two. And you might ask, why is this and can we better it? And the second thing is, as I told you, okay, for 2-dimension, we just have the stationary case. So what is with the instationary case? And this will precisely be what I want to tell you, namely small holes, meaning alpha is larger than the dimension, the 2D instationary case and the 3D instationary case for a beta gamma. You shouldn't be surprised that here is gamma larger than 3 and not gamma larger than 2. This will be then on my very last slide why we probably cannot go get better. So this is what I want to show you. And a very general idea for this homogenization stuff is, okay, you want to have convergence of some function. Of course, if you want to have, so I mean, it's calculus 1, the convergent sequence is bounded, so you need some uniform bounds in your functions which are involved. Once you have this, you get a convergent subsequence, weakly, but okay. And this is kind of the compactness argument, which somehow works more or less independent of the size of the holes. The second step would then be to identify the limiting system. And for this, you say, okay, I have a guess which my limiting system will be. But essentially, you can just work in the perforated domain, meaning you have a test function on your final domain, and you need to cut it off in a suitable way to your perforated domain such that you can insert it as a test function in your momentum on all these equations, and finally pass to the limit. And to pass to this limit, you have to show that the error which comes from the difference of these two vanishes as epsilon to 0, and this vanishes is precisely related to small holes. For critically sized holes, this error will not vanish and will give you then essentially the Brinkmann term, which you will see. But for small holes, this shall vanish. And the tools to be used for this, well, for uniform bounds, you essentially can get from the energy inequality, but it's not really enough, as we will see in a moment. And therefore, so it's not enough to really get a suitable convergent behavior for the density. And to increase this behavior or to increase the integrability, you need the Rogowski operator, which is essentially the inverse of divergence. And you need good bounds on it, so essentially uniform bounds. And to ensure this, this gives you precisely the limitations on your adiabatic exponent and the size of the holes. And the second thing, that your approximations are good approximations in the sense that their error vanishes in some Sobolev space, gives stronger limitations on your shape parameter. Essentially, what you get for bounds is that alpha is larger or equal than something, and in order to give this approximations good, you will get alpha strictly larger than what you had. So this is the way to go. And how we go it? Well, I will not give you a precise definition of weak solutions since we essentially don't need it. But what you have, or what you can show, is that the regularity of your velocity and of your density is essentially as you would expect. So L2 in time, H10 in space, and rho should be L infinity and L gamma respectively, even continuous in the weak topology. But these are essentially the spaces we are working in. And the energy inequality, which is fulfilled by some by well-constructed weak solutions, looks like this, which is also what you would expect. So the kinetic energy, the potential energy coming from the pressure, some fractional energy or friction energy, if you wish, like, and it shall be, of course, bounded by the initial data plus the force. And from this, playing a little bit around with this guy and shift it to the other side, and you use a Grunwald type argument and all the stuff, you get precisely that U is uniformly bounded, meaning independent of epsilon in its space, and rho as well. So that's fine. But the problem is that rho is bounded in L gamma. And if you see the pressure, which is precisely rho to gamma, then it's just bounded in L1. And then you're screwed because L1 is not reflexive, so you cannot get a weakly convergent subsequence, and you need to do something with the pressure. And this is precisely the higher integrability, and for this you need Rogowski's operator, which, like I said, is kind of the right inverse to the divergence, so it gives you the function back you insert it in. And well, this is just some compatibility condition. And of course, you would like that this operator is bounded, and you need to know how this constant precisely looks like. And because it's so important, and we will use it many times, let me say something about it. Yes, large enough. And just a little bit how to construct this. Well, we start with the function in the perforated domain. You prolong it by 0 inside the holes to get something in the domain which is epsilon independent. And now you don't have any epsilons anymore. So you apply a standard Bogovsky theorem, which exists to find some function that vanishes on the very outside and gives you precisely this back, what you want to have, and you get a good bound. The problem is that you are at this point not done, because this function v just vanishes on the outer boundary, but you rather want to have a function that vanishes also on the holes. And for this, well, you can say, okay, just do it naively. So we cut it down to 0 and then we are done. Well, but this changes the divergence. And if you do it a little bit more, let's say, more clever, the construction idea would then be to go from this v near its hole to its mean value, so somehow cut off all its oscillations such that you are essentially constant around each hole. And from this constant, then you cut it off to 0 with using some local Bogovsky operators and so on. This can be done. I will not talk about this too much. But the functions which are involved, these cutoff functions, are Green's functions between your hole and some safety distance. And I will come back to this and what is really meant between with this Green's function. And finally, if you use them, you can see that your Bogovsky operator looks like 1 plus, which is essentially the gradient, plus some constant, which gives you the function back. And it's not really important to remember how this looks like. Important is that we have it explicit. And I will probably go just to the 3D case to explain you what happens. And I mean, let's rule out those borderline cases. So let's focus on this case where Q is, say, strictly larger than 3/2. What it tells you is that the hole size A epsilon is very small, meaning A epsilon divided by epsilon, so this ratio inverted, gets to 0. And if Q is larger than 3/2, then you get here exactly a negative. So this bracket or this absolute value here is simply bounded by 1. And what remains is this. And this is precisely the correct thing you would expect, because this guy here, so this I epsilon to the power 3 minus Q is the capacity of one hole, and epsilon to -3 is the number of holes you have inside. So this constant in the sense of capacity is optimal. You cannot improve it. And for the 2D case, it's essentially the same. And once you have this, meaning we now have a good Bogovsky operator, we have explicit bounds on it where we can work with. And how to use this is that you plug in the density in this Bogovsky operator to get some higher integrability. Why is this sensible? Well, if you get in the momentum equation, you get the gradient of the pressure. If you test it against the function, this gradient becomes a divergence. So you want to have the divergence back. And the pressure just depends on rho, meaning you have the pressure, which is rho to gamma, and the divergence of the Bogovsky, which is rho to theta. So essentially you get rho to gamma plus theta, so a higher integrability. And if you play around, you can see that these are the optimal values for those theta. And finally, you estimate all occurring terms quite nicely. And what you will get is an inequality of this form. So rho in the space you wish to have is bounded by essentially the same thing to some smaller power. And from this, you get a uniform bound and a higher integrability. And once we have this, we are essentially finished with the compactness, since we now have a uniform bound on U epsilon, on rho epsilon, and on rho epsilon with a higher integrability, meaning we can pass to weakly convergent subsequences. And I mean, this we then have here. So U epsilon converges to U, rho epsilon to rho. These two come from the energy inequality, like I showed you. This converges weakly in this higher integrability stuff, which comes from the Bogovsky. And from this, it follows that we also can pass to the limit in the pressure. Just that we don't really know that this function here is P of rho. So it's it's another matter which you have to do to show that weak limits and this power law kind of commute, but you can do that. And of course, what you now have still to show, or things to prove, are the limiting equations for U and rho. And like I said, the strong convergence of the density to ensure precisely this, since otherwise you will get the Navier-Stokes equations with some pressure, but you have no idea how it looks like. And I will not talk about the second point, but rather just the first point, since the second is more or less known. And the first point is somehow what we have done. And now we are at this point that we need to cut off our functions, like I said. So you use a test function in the limiting domain, and you need to suitably cut off. Well, the naive idea is, okay, we cut it off. So we take some cutoff near one hole, we shift it to every hole we have, and we simply press our flow down to zero without, okay, I don't care what happens. Of course, you can do that, but the problem is, and the problem which was before, is precisely that you don't really have enough control on the gradient of that. Another idea would be, or okay, you don't have enough control on the gradient of that, and you would rather like it to have it divergence free to kind of get good control on the pressure, since the pressure is usually the most bad guy, let's say. And so in order to turn it divergence free, which are the simplest function we can imagine, which are divergence free, except of constants, well, these are curls or orthogonal gradients. So I rewrite this identity matrix simply by the orthogonal gradient. It didn't change anything. So just rotate everything by 90 degrees, let's say in 2 dimensions. And this looks almost incompressible. The problem is this guy, since we took just some cutoff functions and we have no idea how it looks like. Well, the idea is now, why don't we take the best cutoff function, which we have, and put it inside the gradient and hope if the gradient falls into this best cutoff function, it does not get really bad. And this is actually not an idea of us, but rather an idea of Marco Bravin, which he proposed in the second half of last year for one single hole, and we generalized it to multiple holes. And once you have this, now you can work, okay, which is the best cutoff function, and this is precisely Green's function. And so Green's function, so our cutoff then will look like it's 1 on a hole, and in 2 dimensions, well, Green's function is the logarithm. In 3 dimensions, it's 1 over r, and we want to have it 0 outside. And with some necessary in between, such that it is at least continuous. To be honest, you have to modify it a little bit such that it gets C infinity and so on, but you can do this. And then we do exactly the same what we had before. You shift this function to every hole and you sum it. This is just what I showed you before. And in 3 dimensions, it's a little bit complicated, more complicated, since you want to have a matrix and a curl, but in 3 dimensions, you don't really have an orthogonal gradient, so you need to modify a little bit of construction. And this T is then a matrix, so you need to define what is the curl of a matrix, but you can simply do this as a tensor, such that you say the curl of a matrix acting on a function is defined as the curl acting on the matrix acting of the function. And once you have identified this, you're essentially done. Since now you do the same as in 2 dimensions, we call it the orthogonal gradient of the orthogonal identity is the identity matrix. And once you have this and you use this, you play a little bit around to say that this matrix has to look like this. Of course, it's not unique. You can have gradients, but for us, it's enough to have this. And well, once you have this, you have everything you want. You have a cutoff function, which is in any Sobolev space and bounded in L infinity. I mean, bounded by 1. That's simply its construction. And the crucial point, it's divergence free. Furthermore, it converges strongly in any LQ to the identity matrix. To be honest, it's not completely true. Like, it's written there because you need this epsilon to be slightly smaller, such that it really converges strongly. Otherwise, it would be just bounded. But it's just a matter of notation. And finally, if you compute the gradient, This converges strongly in, I call it, some good LQ functions, which are then connected. I mean, first of L2, which essentially comes from the velocity gradient. And second, you need to handle the convective term. And from this, you get some other Q stuff or some other exponents, and this will then be the good exponent, if you wish. And this strong convergence essentially follows since it behaves precisely by these constants I just showed you before from the Bogowski operator. And now we essentially can end the proof. We have a function which is defined in our limiting domain. We cut it off with this new matrix valued cutter function. We insert it in the momentum equation, and what you simply get is then this. And now, of course, the crucial terms are those three, since, okay, phi epsilon converges strongly, so this is essentially no problem. This is no problem. This, you have a little bit to work, but it's also no problem. And the most crucial terms are this. And to show you how we get it, let's start with the probably most challenging term ever, which is the pressure. But that's precisely why we constructed the divergence free. So you don't have a derivative of this function here, and then you're essentially at the same case as here. So you simply let this go strongly to the identity, the pressure converges weakly, so this integral is fine. The next crucial part is the convective term. And for the convective term, you expand this gradient, and what you get is phi epsilon times the gradient of your test function, which you can see here. And from this matrix scalar product, you shift your cutoff function to the other side by transposing, and you get this. And you need to show that this converges to what you want to have in distributions. And once you have this, then you can get at this term. This you can do by some kind of Aubert-Lyon lemma and all this stuff. This is kind of, let's say, easily to achieve. But what happens when the gradient falls on the test function? Well, this is then the rest term. And you need, of course, to see it vanish because you already have the correct limiting function. So the rest shall vanish. And this is precisely because this gradient function converges to 0 in some good LQ. This is precisely what I meant with this. And in 2 dimensions, this will then force gamma larger than 2. And in 3 dimensions, you get some condition on alpha and gamma larger than 3, which comes from the denominator in 3 dimensions. And the second thing, or the very last thing, is the diffusive part. And you do essentially the same as I showed you here in these in the second and third point. You split it somehow, and this then forces that alpha is strictly larger than dimension, meaning you have small holes. And well, like I said, the remaining terms are similar. And this is the whole proof. Now, on the last slides, I wish to explain you another idea for 3 dimensions. And if you have a look on the paper I wrote with Milan, you will see that what I will show you here just on one slide is the whole paper, in which I showed you the whole talk is just a remark there. So I kind of inverted the paper, but I did it because the idea also works in 2 dimensions. So, but let me give you a brief hint how we can do it with the pressure extension. Well, if you look at the construction of the Bogowski operator I showed you, it's essentially that you get a Bogowski operator in the whole domain, which you have, and then you take this function which you get down to 0. So you restrict it somehow. And this is precisely then a restriction operator, and you can insert so there exist many restriction operators, but one restriction operator will be crucial for this pressure extension. And what it does is you take a Sobolev function in the whole domain and you press it down such that it gets 0 on the holes. It keeps the divergence-free condition. It is bounded by some nice stuff, essentially what I showed you before, like the Bogowski operator. And if you had a function which is already 0 on the holes, it keeps it. And this will be a crucial property, since with this, we can now define a pressure extension to the whole domain D simply by duality. So we define this capital P by restrict our test function and use the gradient of P which we have. And finally, we replace this gradient of small p in rho. We go into the momentum equation, we replace it, we obtain integration by parts and all the stuff. And what you will finally find is that your p epsilon is uniformly bounded in the sum of those two spaces. So one part is essentially a function, and the other part is essentially a distribution, but just in time. But this comes from the time derivative you have in the momentum equation. And yes, and why I said, well, this property is crucial. Well, you want to have a pressure extension, meaning if you go back to the domain d epsilon, capital P shall be the same as small p. And to prove this, this is crucial. So we really have an extension. And once you have bound your capital P and all the stuff, you can essentially do like before. So you take some cutoff function. Essentially, you can take linear cutoff functions. This doesn't matter. You need to be that sophisticated, and you can show the same result as before. So that's essentially everything I wanted to sell you and to tell you. But on the very last slide, I will give you a brief overview what we have done and what is known. Since at the beginning of my talk, I told you, well, we just can go within stationary to gamma strictly larger than 3. But the stationary case is gamma larger than 2. Why is this? And well, then you compare everything you know. For the stationary case, in 2 dimensions, you have gamma larger than 1. For the 3-dimensional case, larger than 2. For the in-stationary case, you have gamma larger than 2, respectively larger than 3. And now we have kind of, so if we identify the time and the space with, let's say, some new RD, where this frac D is simply the space dimension if you're stationary, respectively the space dimension plus time if you're in stationary, you would expect, well, do we really need gamma larger than this new dimension minus 1? I mean, a physics guy would say, well, it holds for 4 values, so it holds forever. And we asked, well, is it really true? And the answer of this is positive. And let me show you why. If you go through everything I just showed you, so this restriction operator, Bogowski operator, cutoffs and all the stuff, you will see that the scaling in epsilon behaves precisely like this, which is not surprising since, as I told you before, this is the capacity of one hole and this is the number of holes. So it's kind of optimal in this sense. The spaces we live in are essentially the same. So rho comes in its space and u comes in its space. And now you have the Sobolev embedding of this H10 into this L2 star, which is given by this. And well, the restriction on gamma essentially comes from the convective term. So let's have a brief look on this. And what you do is, well, you estimate rho epsilon in L gamma, u in L2 star, u in L2 star. So you get 2 times. And the restriction operator back, which then gives you this terribly looking exponent. And what you then do is, as before, you wish that this guy is uniformly bounded. So you insert this exponent up to here, and this then shall be greater than 0, greater or equal than 0. And if you have this, you will find that alpha has to be larger than this fraction. And from this, you have that gamma shall be larger than d, which is precisely what I told you. For the stationary case, it looks similar. You also do Bogowski operator. You find a better integrability of the density with theta is given by this. In 3 dimensions, it's 2 gamma. That's well known. If gamma is larger than 3, and if gamma is between 3.5 and 3, it simply does. So like 3 gamma minus 3, if you wish, that's the most common value one knows in 3 dimensions. And in 4 dimensions, it looks essentially similar. And you do the same. You plug this guy in here. You use the estimates on the convective term you have. And you see that really gamma shall be larger than d minus 1, which is now the correct value since we are stationary. So finally, physics guys are right. It holds for 4 values, and it indeed holds for any value. So gamma shall be larger than this d minus 1, where d is the space dimension, plus 1 if your model is in stationary. So To conclude, our result in this sense seems to be optimal, and to be a little bit pessimistic, it seems to be that it closes the story. And that's really everything I wanted to tell you. So, děkuji za pozornost.